Today's topic is about knocking in SI engines. And what is knocking? Anybody knows what is knocking?
Sir, an unusual sound, sir.
Yes. When you are driving a two-wheeler, you might have mostly like prominently you can hear this sound, unusual sound, right?
Yes, sir.
So this is because of the abnormal combustion, right?
Yes,
so in the
sir.
last lecture, in the last session, we have discussed about the combustion in SI engine. So today we will be comparing both combustion, normal combustion in SI engine and abnormal combustion in SI engine. This abnormal combustion in SI engine we are going to study in detail. That is what we call it as knocking. Okay. So in SI engine during the combustion process, how the combustion takes place, how the combustion is initiated. In the case of SI engine, how combustion is initiated?
Spark plug.
By spark plug. So spark plug will introduce a spark and flame front will be formed. This flame front will travel towards it will be traversing through the air fuel mixture that is there in the engine cylinder. Okay. So now during this process, right, during the combustion process, huge amount of heat is going to be released, and because of the release of the heat, the temperature of the burnt air fuel mixture, right, are products of combustion. After combustion, the temperature of the burnt mixture, that will be very high compared to the temperature of the unburnt air fuel mixture, right? So we are having air fuel mixture inside the combustion chamber. Spark is introduced. Once spark is introduced, ignition starts or combustion starts. So some part of the air fuel mixture is burnt and some amount of the air fuel mixture is unburnt. Okay. So now the temperature of the burnt mixture, that is very high compared to the unburnt air fuel mixture, right? So once the temperature is higher, so pressure is also going to be higher. So the pressure of the burnt mixture is higher than the pressure of the unburnt. So once the pressure is higher inside the engine cylinder, so that pressure will try to spread throughout the air fuel mixture, right? So when the flame propagates, the pressure is going to be transferred through the air fuel mixture, and this process continues as the flame front advances through the mixture, and the because of the flame front moving or the flame that is going to move, the temperature and pressure of the unburnt fuel, so it is going to try to compress the unburnt fuel, right? So thereby the pressure is going to increase and temperature of the unburnt fuel is also going to increase because it is subject to compression by the flame, right? So the flame is going to compress the unburnt air fuel mixture, thereby the pressure and temperature of the unburnt air fuel mixture is going to increase, and once the temperature of the unburnt air fuel mixture reaches the auto ignition temperature or self ignition temperature, then what will happen? Then that will also start to ignite. The unburnt air fuel mixture will also start to ignite. Okay. Now in this animation you can see, now consider that this is the top view of the engine cylinder. So there is a spark plug which is located at the center. Now spark is being introduced at the end of the compression stroke or just before the end of the compression stroke. The spark is introduced. Now as soon as the spark is introduced, combustion is going to take place and the flame is going to move. So here in the animation you can see, so it is moving. So this region, right, this is your burnt mixture. This is unburnt air fuel mixture. Okay, this is unburnt air fuel mixture. So that unburnt air fuel mixture is subjected to the compression, right? So pressure of the unburnt air fuel mixture is going to increase. Thereby the temperature is also increasing. Once if the temperature of the air fuel mixture reaches the auto ignition temperature, then so this will also start to ignite, right? So you will be having a flame front from here as well as from here, right? So both will collide, right? Thereby noise will be produced or vibration are going to be produced. So this is what we call it as knocking. Okay. So when this happens during there are three stages of combustion we have studied in the last lecture. We used to say like ignition lag stage, then the flame development stage, and then the after flame propagation, then we have the afterburning stage. Okay. If this happens, that the pre-ignition of the unburnt air fuel mixture, if that happens during the ignition lag stage, then this problem of knocking happens. Okay. So that pre-ignition, ignition lag stage is very, very important. Okay. So this is what we call it as the knocking. So this knocking we will study in detail. Okay. So here you can see some of this image shows that this is the flame that is propagating from the center, and this is the engine cylinder wall. Okay. This is the cylinder wall, and these are the places where we have the unburned air fuel mixture which reaches the auto ignition temperature, and as soon as it reaches the auto ignition temperatures, then from here also the propagation of the flame starts. Okay, so these two flame will collide, thereby shock wave will be generated, and this phenomenon we call it as knocking. Okay, so now coming to the normal combustion process, right? Most of the times we will not have this knocking, only during certain time period we will be having this knocking. So during normal combustion process, the flame that is being introduced, the flame that is being initiated by the spark, that flame will travel across the combustion chamber in an uniform manner. When it is moving in an uniform manner, then we don't have any problem of knocking, right? This abnormal combustion will not occur. So now you refer this diagram, right? So this spherical shape, whatever we have represented, right? This is the flame. Okay, so initially we'll be having only the air fuel mixture inside the engine cylinder. So now assume that I'm going to introduce spark from here, right? Or the flame front is going to move from here from point A. From point A, flame front is moving, and as it is advancing, so the combustion of the unburned air fuel mixture is going to take place. Okay. Now, for normal combustion process, we have studied the P theta diagram, right? The cylinder pressure and crank angle diagram, right? So this is your normal during normal combustion process. This is the variation of pressure inside the cylinder for crank angle turned. Okay. So this is the place from where the ignition starts. Right, point A we have studied there in the previous lecture. Then it reaches the peak. Then after burning starts. Okay. So now during the normal combustion process, the flame travels across the combustion chamber from A to D up to this. Okay, from A to D complete. Okay, so this is going to be uniform manner, right? From A to D, the flame is going to travel. Now the temperature of the unburned air fuel mixture, when it reaches the auto ignition temperature only, when we are going to have the knocking problem, right? So this knocking problem happens only when the unburned air fuel mixture reaches the auto ignition temperature. What are the possibilities for this air fuel mixture to reach the auto ignition temperature? There are three ways by which the temperature of this increases. The air fuel mixture, unburned air fuel mixture, whose temperature increases by three means. First one is like the advancing flame, right? This is the flame which is advancing in this direction. This compresses the unburned air fuel mixture. So because of this compression, the pressure of the unburned air fuel mixture increases and temperature also increases. This is one reason. And the second reason is that this flame front that is moving, which is advancing into the unburnt air fuel mixture. So this is at a higher temperature, right? So this flame which is moving or advancing, so that is at a higher temperature because of the exothermic reaction of the combustion. So from here to here, heat transfer will occur. From the burnt mixture to the unburnt air fuel mixture, heat transfer occurs, thereby the temperature of the unburned air fuel mixture increases. This is the second way. And the third one is like, when the third reason is that, so from here within this unburned air fuel mixture also, the pre-oxidation or the pre-flame oxidation starts, or once it reaches the auto ignition temperature, from here also the pre-flame oxidation within the unburnt air fuel mixture also starts. So thereby the temperature of this increases, right? And as a result, from here also the flame front or the flame will propagate. Okay. So these are the reasons by which the temperature of the unburned air fuel mixture increases. Okay. As a result, we are going to have the knocking. Right. So even though we have discussed all these factors, right, for the increase in temperature of the end of the charge, that means the unburned charge. Okay. So in spite of these factors, if the temperature of the end charge had not reached if it is not going to reach the self-ignition temperature, then we don't have the problem of knocking. Okay, the charge will not undergo auto ignition, and the flame will advance further from the diagram. If you see, if this is not going to reach the auto ignition temperature, then the flame that is advancing, it is going to continue advancing further till the and the complete combustion of the unburned air fuel mixture is going to take place without any knocking, right? That is in the usual process. Now instead, the other possibility is that now assume that this unburnt air fuel mixture that has reached the auto ignition temperature, right? So now if it has reached the auto ignition temperature, then what will happen? Knocking occurs. Okay, this is during certain cases this knocking occurs, right? Whenever we are deviating from the normal course of combustion, right? So because of knocking, what will happen? If you are going to have knocking in the engine, then you will be having decrease in performance of the engine, because we are going to lose a lot of brake power, right? Because of this vibration or the detonation or the knocking that is present inside there. So that this is a shock wave that is being generated, right? The power of the fuel is not utilized in a proper manner, right? So we will be having loss of power. And also other problems are like, see, when this knocking is going to occur, the different parts of the engine cylinder will be at different temperature. Okay, so you will not be having the uniform temperature throughout the engine cylinder. So if you are going to have some hot spots within the engine cylinder, mostly your exhaust valve and the spark plug, these are the places where we will have the higher temperature compared to all other places inside the engine cylinder, right? So the spark plug will have higher temperature, exhaust valve will have the higher temperature, and there are other possibilities in some of the regions also you can have the higher temperature. Wherever you are having the higher temperature, then whenever the air fuel mixture it enters into the engine cylinder, then the pre-ignition can happen, right? So that pre-ignition is also a problem. Okay, so when the shock wave is generated during knock, then temperature of this is going to be very high. At higher temperature, we will have the problem of NOx. Okay, so the NOx emission is because of the higher temperature, right? If the combustion temperature is too high, then NOx will be found, because for combustion you are going to supply both fuel and air. In the air we are having nitrogen, and in the air we are having nitrogen, and it also contains oxygen. So at a higher temperature, this nitrogen and oxygen it combines and it forms the NOx. Okay, so other problems because of knocking are, we will be having noise and vibrations of the engine will be there, and as this continues, the failure of the mechanical components may occur, or the damage to the mechanical components of the engine will occur. Okay, so these are the problems. Now let us see in detail how this knocking is happening. Now let us say a flame is being introduced. Assume that this is the point A from where the flame is spark is introduced by the spark plug, and the flame propagates, or the flame advances, right? So assume that it has reached this B dash, right? The flame has reached here. Up to this we have proper combustion, right? And as a result of this advancement, and because of the heat transfer from the flame front, the temperature of the unburnt air fuel mixture has increased, and it has reached the auto ignition temperature, right? So now what will happen? This air fuel mixture that has reached the auto ignition temperature, so this will also start to ignite. Okay, so in the meantime, so the fuel that is advancing from here, from point A, it can go still further little bit up to C dash, right? And it is not reaching the point D, and this has started igniting. Auto ignition of the unburned air fuel mixture has started. So from here also flame is going to come, from here also flame is coming, so both are going to collide. So when these two collides, then shock wave is going to be generated, right? So shock wave is going to be generated. Sir? Yes.
Can you again explain what happens between B and C?
Yeah. See we are introducing spark at point A. Let us say from the spark plug, the spark is introduced at point A. So here everywhere we are having air fuel mixture. So now once the spark is introduced, ignition starts, and the flame is going to advance towards the unburnt air fuel mixture, right? From here the ignition starts, and the flame has to move, it has to travel inside the unburnt air fuel mixture. When it is going to travel, what is going to happen? It is going to compress the unburnt air fuel mixture. When it is going to compress, its pressure is going to increase, and temperature of the unburned air fuel mixture is going to increase. Also this flame front is at a higher temperature, right? The flame that is propagating, that is at a higher temperature, so there will be heat transfer from here to here. So thereby the temperature of the unburned air fuel mixture will increase. That limit, when it reaches the auto ignition temperature of the air fuel mixture, that means without even having a flame or a fire, without even having a spark or a flame, the fuel will undergo combustion. Right? That we call it as auto ignition. Right? So there is a temperature limit. Beyond that, if the temperature of the air fuel mixture reaches or above the auto ignition temperature, then automatically the air fuel mixture will undergo combustion. So that is what is happening here. So the flame front is moving here. Before the flame reaches the complete end, the last end, the end charge that is there at point D, right? This charge that is present in this region, it has reached the auto ignition temperature. Once it reaches the auto ignition temperature, so in the meantime, from here also flame is going to propagate. Already flame is propagating from here, from A towards the end of the engine cylinder, whereas from here also the flame is propagating. So both these flames will collide. When these flames collide, then shock wave is going to be generated. Both are in the opposite direction, right? So shock wave is going to be generated, and as a result, inside the products of combustion, no, that will be subjected to both compression and expansion, right? That will be subject to the because of the shock wave, the products of combustion are going to be subjected to both compression and rarefaction, and this creates a lot of disturbance, and this will create the shock waves will send the shock waves will send a huge amount of force to the walls of the combustion chamber, and as a result it is going to vibrate. So it is going to vibrate at the rate of almost 5,000 cycles per second. Right, these gases, it is going to vibrate, or the frequency of the gases is going to be something around 5,000 cycles per second. Right. So that means what? So there is a race between, or in simple terms you can say there is a race between the flame that has initiated at the beginning and the pre-ignition reaction that is happening because of the reaching the auto ignition temperature. So this flame and this flame, before this flame comes here, it should reach the end of the combustion chamber, right? All the air fuel mixture that is present inside the engine cylinder has to be completely combusted by the initial flame that has been formed, right? So thereby we can have the complete combustion. Okay. So this shock and this shock should not, this flame and this flame should not collide. Okay, this is what we call it as knocking. So if knocking happens, then your P theta diagram, right? If the P theta diagram, if you watch carefully, then after reaching that your peak pressure, this is the point at which the peak pressure is there, and there is auto ignition temperature reached for the unburned air fuel mixture, and from there the flame also starts propagating, and these two flames collide, right? So here you can see the variation of pressure inside the engine cylinder, right? So this variation of pressure, this is unwanted and this is undesirable, right? Because it is going to vibrate and it is going to create noise, and it is also going to damage the engine cylinder parts. Okay. Now this knocking in SI engine, which I have told you, like after the introduction of the spark, the flame advances, and once the temperature reaches the auto ignition temperature, then the auto ignition temperature of the unburnt air fuel mixture, then knocking happens, and as a result there will be lot of variations of the pressure inside the engine cylinder, right? Okay. So now what are the main reasons for knocking, right? There are two important reasons for knocking. The knocking could arise because of the fuel properties, the type of the fuel that we are going to use, the fuel properties, and the engine operating conditions. So these are the two main conditions, right? And in detail we are going to study about various factors that are responsible for the knocking, right? So there we'll say three different factors are there. Okay. So now coming to the fuel properties. The fuel properties, if I say, if you are going to have the fuel with low auto ignition temperature, right? And you consider a fuel which is at a higher auto ignition temperature. If the fuel is having higher auto ignition temperature, then the heat transfer from the products of combustion to the unburnt air fuel mixture, that will not increase the temperature, or that will not make the unburnt air fuel temperature to go beyond the auto ignition temperature, because its auto ignition temperature is higher, right? If the auto ignition temperature of the air fuel mixture is higher, let us say that I am having a fuel whose auto ignition temperature is higher, then the chances for knocking is less, right? So the chances for knocking is less. Also, the ignition lag, the moment we are introducing the spark and the first flame that starts, that we call it as the ignition lag. If the ignition lag is too long, then what will happen? Then the peak will appear too far away from the TDC. peak will not be so closer to the TDC. The peak pressure will happen too far away from the TDC, and thereby we will have proper combustion. So knocking will not happen if the ignition lag is long. Whereas if the ignition lag is very too short, right? This is a start, and this is the ignition, and this is the spark introduction, and this is the start of the ignition. Then what will happen? The peak pressure will be reached here, and peak pressure is going to be reached at TDC, and in the meantime, then the auto ignition temperature of the air fuel mixture is going to be reached, and thereby the knocking will start. Okay, so your auto ignition, your ignition lag should be long, and the auto ignition temperature should be higher. So if there is knocking in the SI engine, see, these are some of the detrimental effects, right? These are the disadvantages, right? So the shock waves that are being generated during the knocking process are the knocking combustion, unwanted combustion, or abnormal combustion. These shock waves will break the lube oil that is sealing the piston and the cylinder. This is the piston, and this piston is going to be inside the cylinder liner, and the in between the piston and the cylinder liner, or let us say the piston ring and the cylinder liner, to be correct, there will be contact between the piston cylinder liner and the piston ring, right? So there we are going to have the lube oil. So if this knocking happens, then the thin film, right, of lube oil that is present in the cylinder wall, so that is going to get affected, right? So because here inside this very high pressure is there, so this layer of lube oil present is there, that is going to get affected. So thereby there will be contact between the piston ring with the cylinder liner. So the friction is going to be higher, right? So as the friction is going to be higher, then there is going to be a lot of heat generation, right? And there is a chance for the piston to seize. Right? All this happens, right, if the engine is going to knock. And the high pressure and temperature, right, because of the knocking inside the engine cylinder, right, above the piston, the high pressure and temperature, that will result in pitting action on the surface of the piston, right? You will be having a pitting action on the surface of the piston as well as on the cylinder liner also, right? In the cylinder wall also, we will be having the pitting action, right? Here you can see there will be erosion of the parts because of the pitting action of the products of combustion as a result of the knocking, right? So this there will be material removal because of the pitting action. Okay, material will get eroded from the piston as well as from the cylinder wall. Okay, so and this shock waves also cause the whole engine structure to vibrate and resonate. Okay, so most of the passengers, they feel it discomfortable, right? So the passengers, they used to object when there is discomfort. Okay, and if the knocking is going to sustain, right, the engine is going to be operated with knocking for a longer time period, that will finally lead to the complete failure of the engine, right? So here you can see the pitting in the your cylinder wall. This is pitting in the piston, okay, because of the knocking. So these are some of the detrimental effects of knocking. Okay, so now coming to the factors that affects knocking, right? So there are the factors that affects knocking are basically classified under 3 divisions, right? One we call it as density factors. Under density factor, these are the parameters responsible for knocking in the engine. So density factor, under density factor we have compression ratio, we have mass of the charge inducted during the suction stroke, and the inlet temperature of the charge that is inducted during the suction stroke, and the combustion chamber wall temperature, right? And the spark advance, that is also a parameter, and the power output from the engine. Higher the power output, then what will happen to the knocking. So all these parameters are directly related with the density of the air fuel mixture. So all these parameters are directly related with the density of the air fuel mixture, and we will study all these parameters in detail, how it is going to affect the knocking. And the timing, right? So timing in the factors related to the timing are turbulence, engine speed, distance of flame travel, size of the engine. If the engine size is bigger or the diameter of the engine cylinder is bigger or smaller the diameter, what is going to happen? Then the combustion chamber design, right? The shape of the combustion chamber, and where to locate the spark plug. Whether we have to locate the spark plug on the side of the engine cylinder or at the center, right? So these are the parameters which are directly related to the timing factor. Okay, so these are timing factors. And coming to the composition of the air fuel mixture, right? Under composition of the air fuel mixture, there are two parameters. One is fuel air ratio and octane number of the fuel, right? So these are the various factors that affect the engine knocking. Okay, now let us see one by one. Let us start with the density factor, right? Under density factor, see, there are two things, right? Whatever may be the design factor and the operating condition, right? Any factor in the design and operation of the engine, if it increases the temperature of the unburned charge, right? If it increases the temperature of the unburned charge, then knocking will be there, right? Or any design or operation parameter that directly increases the density of the air fuel mixture, then knocking will happen, right? The density of the air fuel mixture increases, or if the temperature of the air fuel mixture increases because of the any of the parameters of the engine while operating or during the design, then that will lead to knocking. Okay, so density has to be maintained properly, it should not increase. So now let us say considering the compression ratio. Compression ratio of the engine, let us say you are having a variable compression ratio engine, right? In the thermal lab, assume that we are having a variable compression ratio engine. So where you can adjust the compression ratio. So now if you are going to increase the compression ratio, then what will happen to the density of the air fuel mixture? Yes. When we increase the compression ratio, what will happen?
Density will increase, sir.
Yes, density will increase. So if higher the compression ratio, that will increase the density. So this increases the pre-flame reaction. That means the unburnt air fuel mixture that will start undergoing pre-flame, right? From there it will start, and this will result in the knocking, right? This will result in the knocking. So this is one reason. So your compression ratio we have to maintain properly, right? So when you are going to design or by conducting experiments, they will identify the optimum compression ratio to avoid the knocking in the engine cylinder. And now let us say you are going to increase the mass flow rate, right? We are going to increase the mass flow rate of the air fuel mixture during the suction stroke, right? So now what will happen to the density? Your volume is going to be same, right? The volume that is available inside the engine cylinder is same, but you are going to send more amount of fuel in, right? You are going to send more amount of charge, air fuel mixture, we are going to allow in. What will happen to the density now?
Increase.
Yes, density?
Increases.
Volume is same, density is mass by volume. Volume is same, mass is more. What will happen to density?
Increases.
Increases, yes. So if density increases, then knocking will occur. So reduction in mass flow rate during induction decreases the density, and thereby it decreases the knocking. Okay. And now these days we have the concept of supercharging. Correct? Turbocharging, supercharging. What is supercharging? In smaller volume, if you are going to accommodate more amount of fuel, right? In smaller volume, with the same volume, let us say, you are going to allow more amount of air fuel mixture and combustion takes place. Then what will happen to during supercharging? What will happen to the density of the air fuel mixture?
Increases.
Increases, right? So let us say if the engine is knocking, then you should not have supercharging. Okay. Reducing supercharging will reduce the knocking. So if you are going to have supercharging, then the chances of knocking or the tendency for knocking is going to increase. Okay. Then the other density factors. If the inlet temperature of the charge, right? If the inlet temperature of the charge is higher, when the air fuel mixture enters into the engine cylinder, it is at a higher temperature, right? If it is at a higher temperature, then what will happen? The auto ignition temperature will be reached quickly, right? During the compression temperature, it will let us say that at a higher temperature air fuel mixture is entered, and now the combustion has started. Now the flame is advancing towards the unburned air fuel mixture. Already during the intake itself, its temperature was higher. Now there is heat transfer from the advancing flame to the unburned air fuel mixture. So it will reach the auto ignition temperature quickly, and it will lead to knocking. Okay. So, and remember, your inlet temperature when the fuel enters, it should not be too low also. It should not be too high also. If it is too low, then what will happen? The vaporization of the air fuel will not occur properly. For vaporization of the air fuel, for better mixing of the air fuel, we should have proper vaporization. That vaporization of the fuel depends upon the temperature. So if the intake temperature of the air fuel mixture is too low, then it will affect the vaporization. So you will not have the complete combustion. So we need to have an optimum temperature at which air fuel mixture enters into the engine cylinder. Okay. Now again another parameter is the cylinder combustion chamber wall temperature. Your combustion chambers wall temperature or the engine cylinders wall temperature, right? So in order to prevent the knocking, we should not have hot spots in the engine cylinder. Inside the combustion chamber, there should not be hot spots. I have told you like some of the hot spots. One is spark plug, right? Because it is going to, from there only the combustion is going to start. As soon as the spark is introduced by the spark plug, from there the combustion is going to start. So that the spark plug will be at a higher temperature. That is a hot spot. And the exhaust valve through which the fuels are going to leave. Okay, so that is going to be another hot spot. These are the two hot spots in the combustion chamber, right? And when the unburned air fuel mixture or the end gas or the end charge, when it comes in contact with the hot spot inside the engine cylinder, then auto ignition takes place. Okay. So your cylinder combustion chamber wall temperature should not be higher. Okay. And the other factors, right? Other density factors is retarding the spark timing. If the spark timing, if you are going to vary, right? I have told you that spark has to be introduced before the piston reaches the TDC, right? Before it reaches the TDC, we have to introduce something around. I have told you in the last lecture we have discussed about the spark is introduced at 20 degrees C before TDC. Okay, and we have also discussed like if the up to maximum of 30 degree before TDC is allowed. Okay, now here you see. So this P theta diagram, right? This P theta diagram is a normal combustion process. This indicates a normal combustion. Okay. During normal combustion, here if you see the spark is introduced at 28 degrees C before TDC. This is TDC. So let us say this is 28 degree. So 28 degrees C before TDC spark is introduced, and there is a complete combustion. Normal combustion takes place. Now the spark is now the spark it has happened at 30 degrees C. Right, that means they have increased, right? So before the piston reaches the TDC, 30 degree before the spark is introduced. So once the spark is introduced earlier, if the spark is introduced earlier, what will happen? This peak, right? This is too far away from TDC during normal combustion. Now this peak is shifting towards the left. The engine cylinder peak pressure, it is shifting towards the left side. So if it shifts towards the left side, then this knocking phenomenon happens. Okay. Now you consider this case. This is slight knock. If the spark is introduced 32 degrees before TDC, right, too early, then this peak is coming closer to TDC, and the unburned air fuel mixture that undergoes the auto ignition and the knocking occurs. Okay. So if you reduce the spark timing, right, closer to TDC, okay, if by retarding the spark timing, right, so if by having the spark introduction closer to TDC, the peak pressures are reached farther away from the TDC, and thereby you can reduce the knocking. Okay, so spark timing is also very important. And coming to the power output of the engine, so normally in the case of two-wheeler, if you find this knocking, that means you are accelerating. If you want higher power, when you want higher power, when you want higher engine output, then what will happen? The temperature inside the combustion chamber is going to be higher, right? And that results in higher temperature of inside the engine cylinder as well as the walls of the combustion chamber, and thereby the knocking occurs, right? So if the output of the engine is less, then the temperature of the cylinder and the temperature inside the engine cylinder and the combustion chamber walls are less, and thereby the pressure is also less, and the unburned air fuel mixture that will not reach the auto ignition temperature, and you can avoid the knocking. Okay. So combustion wall temperature is also a parameter similar to your power output from the engine, right? So higher the wall temperature, then chances of knocking is going to be higher, right? And coming to the so these are some of the parameters that are responsible for knocking. Okay, and coming to the time factors, right? So if you see density factors, we have started with the compression ratio, right? Higher the compression ratio, density is going to be higher. Then amount of mass that is entering is going to be higher. Then the density is going to be higher. That will lead to knocking. Inlet temperature, if it is higher, then knocking will be, chances of knocking is going to be more. Then combustion wall temperature, then spark advance, right? So if you are instead of 28 degrees C before TDC, if you advance the spark, that means like at 32 degrees C before TDC, 32 degree before TDC, if the spark is going to be introduced, then we are going to have the knocking, right? If the power output is going to increase, there also we are going to have the chances of knocking is going to be higher. Now coming to the time factors, right? Turbulence, engine speed, all these are all time factors. Coming to the time factors, so now increasing the flame speed, right, or increasing the duration of the ignition lag, okay, these are all advantages, right? So then what will happen? The time period during which the unburned air fuel mixture are exposed for the higher temperature or auto ignition temperature is going to be less. Thereby we can reduce the knocking, right? So your flame speed should be higher, and the ignition lag, that is ignition lag is your first stage, right? Your flame preparation stage. So that should be wider. If it is too long, that duration is going to be higher. Then knocking you can avoid. Now coming to the time factor, the first parameter is the turbulence, right? So all these parameters we are going to link with the flame speed and the duration of the ignition lag. So if it is turbulence, so if assume that you are going to increase the turbulence, when the turbulence is increased, then the flame speed, right, that is also going to increase, right? Increase the turbulence will increase the flame speed, and this reduces the time available for the end of the charge to auto ignite, right? So that is going to be less, right? So thereby we can avoid the knocking, right? So if the, let us say we have studied the air motion. In the air motion or the air fuel mixture motion, like this tumble, swirl, all those things we have studied. If you are going to have better turbulence, better mixing of the fuel is going to be there, and the flame is going to be traveling at very high velocity, and thereby if it is going to travel at a very high velocity, then the time available for the unburned air fuel mixture to reach the auto ignition temperature is, the chances are going to be less. So thereby we can reduce the knocking. And similarly coming to the engine speed, if you are going to increase the engine speed, then it increases the turbulence. Considerably it is going to increase the turbulence, and that will result in the increased flame velocity, and that reduces the chances for knocking, right? And when the travel is, when the spark is introduced, flame is formed and the flame is going to travel. The flame distance traveled by the flame, that should be smaller. You should design an engine in such a way that the distance traveled by the flame should be minimum, right? So if you are going to reduce the distance traveled by the flame, then the time available for the unburned air fuel mixture to reach the auto ignition temperature is going to be less. Thereby we can avoid the knocking. Okay. So it should not travel if the diameter of the engine cylinder is diameter is more, right? Then what will happen? Then the flame has to travel a longer distance, right? In the meantime, the unburned air fuel mixture will reach the auto ignition temperature, and chances for knocking are going to be there. Okay. So coming to the engine size, right? Coming to the engine size, this is similar to your flame travel distance, right? If the engine size is smaller, for a smaller engine, the time required for the flame front to travel the end of the charge is going to be less, right? And you are going to have complete combustion, so there is no chances for the knocking, right? So that is why in the case of let us say most of the SI engines, two-wheeler SI engines, are generally the diameter of the cylinder is going to be 150 mm, right? That means smaller the diameter, then the distance traveled is going to be less. Therefore you can reduce the knocking. And the combustion chamber shape of the combustion chamber is also an important parameter. It should be, the shape should take care of the flame travel distance, right? The shorter the flame travel distance, the distance traveled by the flame is going to be less, then we will have the proper combustion, and knocking can be avoided. So to the extent possible, if you are going to try to have some spherical shape for the engine cylinder to the extent, right, then you can have complete combustion and avoid the knocking. Okay. And coming to the location of the spark plug. The location of the spark plug is another important parameter. So I told you like you can place spark plug either at the center or at the side of the engine cylinder, right? So if the spark plug is located at the center, right, then if it is going to be located at the center, that will result in minimum knocking because the flame can travel easily throughout the air fuel mixture, right? Quickly it can reach the cylinder, right? Or there are other options. Instead of having one spark plug, you can go for multiple spark plug. All right, by which you can have the time available for the unburned air fuel mixture can be reduced, and it will not reach the auto ignition temperature, and we can have the complete combustion. Okay.